Good morning.
Good morning.
So today I want to start talking about chapter 21. And we're getting into the meat of the course right now. So we're talking the whole overarching theme of a huge portion of the class is carbonyl chemistry. And when I introduced the course and overviewed the course on the very first day, I said there are two main classes of reactions of carbonyl compounds that are going to be a lot of our thinking. One of them is reaction at the carbonyl compound with nucleophiles, and the other is reaction of the alpha carbon as a nucleophile, and we'll be learning about that later. But now we're going to really be delving in to the reactions of carbonyl compounds, and particularly aldehydes and ketones with nucleophiles. And we've already gotten this theme, and we're going to see now some variations. So the theme that we've gotten is if you have a carbonyl compound, a ketone or an aldehyde, and you have a nucleophile, and I'm going to describe that nucleophile as a strong nucleophile, or maybe more specifically, we'll say a strongly basic nucleophile, or even a nucleophile that's not quite so strongly basic, even let's say a moderately basic nucleophile. And I'll elaborate on this in a moment. In either of these types of conditions, a carbonyl compound, a ketone or aldehyde more specifically, is electrophilic enough at the carbonyl compound that the nucleophile is going to attack the carbonyl. We've already seen this reaction. Electrons flow from the nucleophile to the carbonyl compounds, carbonyl carbon. You can't have 5 pairs of electrons around a carbon, so concurrently, as electrons are flowing, as the nucleophile is approaching the carbon, electrons are flowing up onto oxygen. And the overall result now is that we have an alkoxide anion. I'll write that as O minus. We have 3 lone pairs of electrons around the oxygen. And in very, very generic terms, because we're going to see a lot of variations of this, but in very generic terms, if we have some source of H+, and remember, of course, I'm going to put it in quotes because you don't have naked H+. It would be a hydronium ion or acetic acid, or we're going to see lots and lots of variations here. Anyway, some source of a proton, some source of H+, can protonate our alkoxide anion to give you an alcohol, like so. And so that's what you've seen already. We're going to see some variations on this, but we're also going to introduce, and this is where things get really meaty, we're going to introduce the reaction of carbonyl compounds with weakly basic nucleophiles. And again, in the most general overview now, I'm going to write this as our carbonyl compound, our ketone or aldehyde, plus a weakly basic nucleophile. And again, it's a little hard to generalize, but let's envision some species that in general is not going to have a negative charge. Not all strongly basic nucleophiles have negative charges, but many of them do. Not all weakly basic nucleophiles don't have negative charges, but let's say in general they don't. And we'll envision that that nucleophile still has an electron pair to share. You've seen weakly basic nucleophiles before. Alcohols, water, those are weakly basic nucleophiles. And so along with our weakly basic nucleophile, imagine for a moment that we have some source of an acid catalyst that we'll call BH+. And so imagine now for a moment that the nucleophile, because the carbonyl compound, the ketone or aldehyde, is only moderately electrophilic, imagine for a moment that the nucleophile isn't nucleophilic enough to attack the carbonyl. But you can set up an equilibrium where the base protonates the carbonyl. And so I'll write this as an equilibrium where now you protonate the carbonyl. And of course, you still have your nucleophile H with its lone pair. And now you have your base, your conjugate base. All right, at this point, now your carbonyl is a lot more electrophilic. Remember, something that's electrophilic wants electrons. In general, if you've got a positive charge, it's going to want electrons all the more. And so now your weakly basic nucleophile says, wow, this guy really, really wants me. I'm going to share my electrons. And so we can envision electrons flowing from the nucleophile to the carbonyl carbon, the protonated carbonyl compound, just as they did before. But the exception, or the difference, is it's a lot more electrophilic. And again, just as before, we can't have 10 electrons around a carbon. So as electrons are flowing from the nucleophile, we're putting electrons up onto the oxygen atom. And at this point now, we have our tetrahedral species, but it's already protonated. And we still have our base. And our positive charge now is on the nucleophile. And so at this point, the base, the conjugate base of the acid catalyst, can pull off the proton. And if this sounds a little bit abstract right now, don't worry, because we're going to see lots of concrete examples. And in many of these concrete examples, some of them, not ones that we'll see today, but later on, this species can undergo further reaction. And so over the course of the next 3 lectures, this lecture and next week's lecture, we'll be exploring these themes in carbonyl chemistry, and specifically in the chemistry of aldehydes and ketones. All right, so that kind of serves as the overview of what we're going to see over the next few weeks, over the next 3 lectures. So let's start in by talking about aldehydes and ketones more specifically, and talking about their properties and how we name them. Naming by now should be pretty easy for you. You can recognize the idea of getting a principal, identifying a principal chain. A 4-carbon chain, for example, in this compound tells us that's a derivative of butane. And so to name it, we just call it butanal. The aldehyde can only be at the end of a chain, so we don't need to go ahead and put any number to it. On the other hand, if we have a ketone, let's take this example. Now, of course, you can have a ketone's carbonyl at various positions. We've got to identify the principal chain. The longest chain in this molecule is a 5-carbon chain. We look at the molecule and we say, okay, I'm going to try to number it, so I put the carbonyl at the lowest position. So that's at the 2 position. And we have a methyl group at the 3 position, and we use ONE to indicate a ketone. So this compound is 3-methyl 2-pentanone. And really, that's all there is to naming compounds by way of the IUPAC names for aldehydes and ketones. Now, there are so many aldehydes and ketones that have common names that we would maybe never even use the systematic name. So for example, if I looked at this ketone, who knows what this ketone is? Acetone, exactly. I think I'd be very hard-pressed to say propanone for it, just because its common name, its nickname, is so ubiquitous. If I did say propanone, because the only position the carbonyl could be at is the center position, I wouldn't even have to put a number on it. In general, small compounds that have some history to them have trivial names, have common names that usually become the ones that roll off people's tongues. This aldehyde here, anyone? Formaldehyde is 1 carbon. And what do we call, what's the 2-carbon? What's the 2-carbon acid? Ethanol is, right, the 2-carbon alcohol. And CH3COOH is acetic acid. And so this is acid aldehyde. And again, its real name or its systematic name is ethanal, but nobody is going to call it that unless they're naming things as a substituted version of it. This aldehyde here, benzaldehyde. Even though its systematic name would be phenylmethanal. Anyway, for the most part, nomenclature is dull as dishwater, other than perhaps systematizing in your mind the anatomy of a compound. So let's take a moment to talk about some of the properties of aldehydes and ketones. You've probably all had the opportunity to work with acetone. If nothing else, it's a common solvent that's used to wash your glassware. If any of you are wearing nail polish out there, you've probably used it and smelled it along with ethyl acetate and nail polish remover. It's a pretty volatile liquid. It's got a boiling point of 56 degrees, so it has a high vapor pressure. As I said, it's a liquid. One of the things that one can do is put properties of compounds into context, comparing them to similar sized compounds. So for example, if I look at a similar sized compound containing just carbon, if I look at isobutane, isobutane by comparison is a gas with a boiling point of -12 degrees. So isobutane, of course, can only have van der Waals interactions among the molecules. It's a nonpolar molecule. Acetone can participate in dipole-dipole interactions. It's got a great molecular dipole to it. It's miscible with water. It even dissolves some inorganic compounds like sodium iodide dissolves very well in acetone. And if we go further, so isobutane has van der Waals interactions, so very little to hold it together. Acetone brings in van der Waals plus dipole-dipole interactions. By the time you get up to isopropanol, your boiling point is even higher. Now it's a liquid with a boiling point of 82 degrees. And of course, there you get hydrogen bonding as well in its interactions. I don't want to spend too much time. We're going to get more of a flavor of reactivity later on as we go. But I want to give you a general feeling that in general, ketones are more reactive than aldehydes. And that kind of makes sense. We're going to see more of it when we talk about hydrates. I think that's where it really brings home the point. But let me just say, compare acetaldehyde versus acetone. So acetaldehyde is more reactive. I'll draw it. Similar purposes. And the main difference in reactivity that I think of is mainly electronic. In other words, your carbonyl in both of these compounds, both in acetaldehyde and in acetone, is reactive toward nucleophiles. But your acetaldehyde is more reactive, more electrophilic because the carbonyl is more electron deficient. Remember, methyl groups are electron donating. So in addition to having the carbonyl dipole, you have one dipole here donating in electrons. And so in the other case, you have two sets of donations. The methyl groups can donate. So you're less electrophilic here. The carbonyl is less unhappy. You also have a steric component. And so between the two of those, the electronics of the donations from the alkyl groups and the sterics of the methyl groups, it's more electrophilic in acetaldehyde. Resonance will also affect things. So for example, benzaldehyde versus acetaldehyde. Benzaldehyde has resonance stabilization of the carbonyl, so it's going to be a little bit less reactive than, say, acetaldehyde. So I will write two electron donating groups here. Versus one for acetaldehyde. All right, I want to take a moment to talk about some of the spectroscopic properties of carbonyl compounds, and maybe the way to do it, since obviously in IR spectroscopy they all have a carbonyl stretch as a defining factor. Maybe the way to do this is to look at sort of differences among them. And so let's talk about IR spectroscopy of typical carbonyl compounds. One way I think keep things straight in my mind when I think about the very subtle differences in carbonyl stretching frequencies is just to keep in mind a progression that in general, as we go from esters to aldehydes to acids to ketones to amides, in general, the carbonyl stretch moves to slightly lower wave numbers, slightly lower frequencies. Esters, a typical aliphatic ester is about 1750 to 1735 wave numbers. A typical aldehyde is about 1740 to 1720 wave numbers. A typical carboxylic acid is about 1725 to 1705 wave numbers. A typical ketone, or let's say, yeah, a typical ketone is about 1725 to 1700. And a typical amide is about 1690 to 1650. So outside of amides, all of these sort of end up in overlapping ranges. And as I said, these are kind of general values. In other words, if you have conjugation, like benzaldehyde, that's going to shift the carbonyl frequency by several tens of wave numbers. So in other words, you look at these bands, and they're not purely diagnostic on their own. But then there are other factors that clue you in. We talked, for example, about carboxylic acids. And we said it's pretty hard to miss a carboxylic acid in the, whoops, I have managed to swap ester aldehyde ketone, pardon me, acid amide. So if we look at, say, a ketone versus an acid, there's not a heck of a lot of difference. They fall essentially in the same range. But a carboxylic acid has a very well-defined OH stretch that's really broad from about 3,500 to about 2,500. I shouldn't say well-defined, but very pronounced. Remember, I drew it out for you before. It's this big, ugly, encompassing blob that starts well above the CH stretches and ends well below the CH stretches, may obscure them, and has kind of little features to it. It's pretty hard to miss, as long as your molecule isn't gigantically huge, in which case the carboxyl group is only a small part of the molecule. So for the most part, if you saw a peak at, say, 1715 wave numbers, you'd say, well, that might be a ketone or it might be an acid, but then you look down at the region around 3,000 and you say, oh my God, there's this big blob here. It's got to be a carboxylic acid. So similarly, there are other corroborating features, albeit sometimes more subtle. For example, esters, you can sometimes, not always, because the fingerprint region is pretty crowded, you can sometimes see the CO bond single stretch at about 1,300 to about 1,100. But again, there's a lot of stuff there, so I'll put this sort of in parenthesis as you might be able to pick it out. So you get a little hint. Of course, NMR spectroscopy brings in other hints. We talked about a CH2 next to an oxygen in an ester, and we say that's so about 4 parts per million, and so that would clue you in. Aldehydes also have little hints. For example, the carbonyl, the aldehyde hydrogen gives you a couple of bands from the CH stretch. The CH stretch typically shows you right at the lower edge of the CH stretching region, about 2820 and 2720 shows a couple of bands associated with it. They're sometimes hard to pick out because they're right on the lower edge of all of the other CH stretches, but if you look hard, sometimes you can pick it out. However, there are going to be other spectroscopic features, for example, in the NMR spectra, that would clue you in, say, to an aldehyde, the presence of the CH group, which we'll talk about in just a moment. All right, as I said, there are a lot of factors that perturb these sort of general aliphatic carbonyl stretching frequencies. So one of the big things is conjugation, as I just mentioned. So for example, if you take a look at cyclohexanone, cyclohexanone has its carbonyl stretch right in the middle of where you'd expect, right in the middle of where you'd expect for a ketone, right at about 1715. If, on the other hand, you go to cyclohexenone, the conjugation of the double bond with the ketone goes and weakens the CH stretch. It shifts it to lower frequency to about 1685 wave numbers. We've already seen this in talking about and overviewing some of the chemistry of alpha, beta, unsaturated carbonyl compounds when we were talking about cuprate chemistry, and we explained that there are many different resonance structures. One of the resonance structures has single bond character. It's a minor contributing structure, but it shows you how collectively the various pictures of the molecule end up indicating that the carbon-oxygen double bond isn't quite as strong, that it doesn't stretch at quite as high a frequency. This same type of effect occurs in other sorts of alpha-beta unsaturated carbonyl compounds. So for example, if we look at acetophenone, the ketone is also at about 1685 wave numbers. Now, another thing that can change the carbonyl stretching frequency is ring strain. So if you take a look, instead of at cyclohexanone, if you take a look at cyclobutanone, now you've got a four-membered ring. And of course, the bond angles in a four-membered ring are much smaller than in a six-membered ring. In cyclohexane and cyclohexanone, the carbon-carbon bond angles can be essentially what they desire to be. A carbon, sp3 carbon bonded to an sp3 carbon bonded to an sp3 carbon wants to be 109.5 degrees. An sp3 carbon bonded to an sp2 carbon bonded to an sp3 carbon wants to be 120 degrees. But by the time you get down to cyclobutanone, all of your angles are getting forced to be much, much closer to 90 degrees. As a result of that, you're having to use more p character in making up the ring bonds. That leaves more s character for the CO bond. And remember, s orbitals are lower in energy, so that's going to make the CO bond stronger, which in turn means it's going to vibrate at higher frequency. So cyclobutanone ends up having a stretching frequency of 1780 wave numbers. And I'll just jot this as more p character in the ring leads to more s character in CO bond. And that leads to a stronger CO bond. The same effect of ring size. Cyclobutanones are pretty rare. They don't occur commonly. You don't find them in many molecules like, for example, steroids and other sorts of very few natural products, say, contain them. On the other hand, cyclopentane rings and cyclopentanones are much more common. And even in a cyclopentanone, you can see this same effect of a stronger CO bond. So for example, when we compare cyclopentanone to cyclohexanone, our carbonyl stretching frequency is still about 30 wave numbers higher. It's at about 1745. And as you can see, if you only relied on these general CO values and you said, oh, the only thing that's 1750 to 1735 is an ester, so that carbonyl must be an ester, you'd be wrong because there are many factors that perturb it. Ditto if you said, oh, the only thing in that table that's at 1685 is an amide, so it must be an amide. You'd be wrong on those because, again, there are many factors that perturb it. And this is why the confluence of infrared spectroscopy and NMR spectroscopy and good sound chemical and mechanistic thinking and being able to read other subtle clues in the spectrum like a CO single bond stretch or CH of an aldehyde or the not so subtle OH of a carboxylic acid ends up being very important. All right, well, in NMR spectroscopy, there are also some general things to keep in mind. And one of the things that I like to do when I think about NMR is sort of put things in broad classes. Alkyl CHs generally, if there's nothing perturbing them, show up from about 0.9 to about 2 ppm, about 1 to 2 ppm for a methyl group, a methylene group, or a methine group, respectively, more toward 0.9 for a methyl, more toward, say, 1.4 for a methylene, and more toward 1.5 or 2 for a methine. Ditto, if you have a hydrogen that's next to a carbonyl, you tend to have sort of a general area that that hydrogen might be at, sort of generally about 2 to 3 ppm, depending on the type of hydrogen. So for example, a methyl group off of a carbonyl tends to be more about 2 ppm. And again, all of these are approximate numbers, so I'll put little tildes to indicate sort of general. If it's a methylene group, it'll be a little bit further downfield, maybe 2.3-ish ppm. If it's a methine group, it'll be a little further downfield still, maybe about 2.6 ppm. And so this is kind of a good starting point for reading an NMR spectrum. By the time you're having a hydrogen that's directly attached to a carbon that's attached not to a carbonyl but an oxygen, you've kind of moved into the 3 to 4 ppm range. So a CH2 that's, say, part of ethanol is going to be at about 3.4. A CH2 that's part of ethyl acetate is going to be at about 4.1 ppm. The aldehyde CH is another very characteristic feature in the spectrum. An aldehyde CH is typically at about 9 to 10 ppm. One of the things that's interesting about aldehydes is your coupling constants for most J coupling, with the exception of double bonds. Most J coupling is about 7 Hertz. In other words, when you see a triplet or you see a quartet for ethanol, the spacing of those lines is generally about 7 Hertz apart. In an aldehyde, because of the electronegativity and because of the hybridization of the aldehyde carbon, the J coupling ends up being considerably smaller between the adjacent hydrogens. Your J value is generally about 1 to 3 hertz. Now, the implications of that is when you look at a compound that, say, has an ethyl group in it and an aldehyde group in it, you look at the ethyl group and you say, oh, it looks like a typical triplet for the methyl. The lines are in this pattern of spacing that I'm used to. And then you look at the aldehyde and you say, my God, the lines are so close together. What's going on? Well, what's going on is that it has a smaller coupling constant. And so being able to recognize that clues you in, and you can say, I have an aldehyde next to 1 hydrogen, or I have an aldehyde next to 2 hydrogens. I guess the other thing I'll touch on very briefly is your C13 NMR spectrum. The most defining feature of aldehydes and ketones in the C13 NMR spectrum is the carbonyl. Your textbook gives a number of about 190 to about 215 ppm for aldehydes and ketones. The carbonyl of ketones tends to be a little bit more toward the downfield end, a little bit more toward the 210, 215. The carbonyl carbon of aldehydes tends to be a little bit more toward the upfield end, maybe 195 being sort of a typical value for aldehydes. These, of course, numbers are very different than what you see for, say, a carboxylic acid or an ester, where you still have a carbonyl carbon standing out very far downfield, but now it's more like 170 or 180 ppm. Your textbook does a very nice job of reviewing chemistry that you've already learned, and I'm just going to mention a few things on the synthesis of aldehydes and ketones, things that you've seen before in earlier chapters. So when you were learning about when you were learning about alcohols, you learned about oxidation reactions to make aldehydes and ketones, and I mentioned this briefly when I was talking about carboxylic acids. Chromium-6 is a very common oxidizing reagent, often in the form of potassium chromate or potassium dichromate or sodium dichromate or chromium trioxide. A general and indeed old-fashioned and somewhat toxic and carcinogenic recipe for oxidizing secondary alcohols to ketones is to take potassium dichromate or sodium dichromate and sulfuric acid in water, sometimes called Jones's reagent, and that is a general oxidizing agent to oxidize a secondary alcohol to a ketone. Your textbook introduced you to the concept of selectivity. This reagent oxidizes primary alcohols directly to carboxylic acids, but if you take a primary alcohol, RCH2OH, I'm gonna write it a little bit neater here, RCH2OH, and you treat it with the reagent PCC, pyridinium chlorochromate. Often in methylene chloride, you need a non-hydroxylic solvent. You need an anhydrous solvent for this reaction. Methylene chloride does a nice job for this. Then you can selectively oxidize a primary alcohol to an aldehyde. Ketones and aldehydes are in a higher oxidation state than alcohols. Ketones and aldehydes are in a lower oxidation state than carboxylic acids. So for example, if you take an ester with a selective reducing agent like dibal, you can reduce your ester right down to the corresponding aldehyde. And again, I've mentioned this one before. Dibal H or dibal followed by an aqueous workup with water or H3O plus aqueous acid can reduce your aldehyde, your ester directly to an aldehyde. And of course, the other product of the reaction is your corresponding alcohol. Your textbook also reminded you that there are selective reactions to reduce acid chlorides. Acid chlorides are extremely, extremely reactive. You'll learn as we go on to discuss esters and as we go on to discuss other members of the carboxylic acid family that acid chlorides react directly with water. They react directly with alcohols because the chlorine is electron withdrawing and they're very electrophilic. You can selectively reduce the acid chloride down to an aldehyde with a very attenuated form of lithium aluminum hydride. Lithium aluminum hydride in which we've added 3 equivalents of tert-butanol to get this very bulky, very non-reactive lithium tritert-butoxy aluminum hydride, LiAlHOTBu3. And this reagent barely wants to transfer hydride, but the hydride is nucleophilic enough that the very electrophilic acid chloride can be reduced selectively to the aldehyde. And again, you need some type of aqueous workup in this, water or aqueous acid. All right, so that kind of covers reactions that you've seen for reactions in which you're transforming oxidation state without really changing the structure of the molecule. You've also learned about some reactions that transform the structure of the molecule more profoundly while changing oxidation state. So for example, you've learned again in past chapters about ozonolysis. You can take an alkene and treat it with ozone, which you generate by passing an electric discharge, silent electric discharge through oxygen. And then you can reduce the resulting ozonide with dimethyl sulfide, Me2S, or zinc and water. You can reduce the resulting ozonide and you cleave, hence the lysis, you cleave your alkene into 2 carbonyl halves, 2 ketones or 2 aldehydes, or a ketone and an aldehyde depending on what substituents you have on your carbonyl group. Again, by way of review, your textbook reintroduces various reactions of alkynes, and this is all a quick survey of things you've seen before. So your textbook reintroduces the Markovnikov addition of water across alkynes to give ketones. So for example, if we have a terminal alkyne and we treat it with sulfuric acid and a catalyst, typically a mercury catalyst like mercuric sulfate, HgSO4, in the presence of water, we add a mole of water across the alkyne in a Markovnikov sense. The first product is an enol, which we'll be talking more about later. The enol undergoes tautomerization to give the corresponding methyl ketone. Organic chemists are all about control, being able to control chemoselectivity, being able to control stereoselectivity, and being able to control regioselectivity. The natural regioselectivity of addition across an alkene is to put of an alkyne is to put the substituent on the more substituted carbon, and that has to do with stabilization of carbocations. Chemists, for that reason, have developed chemoselective reactions that do the opposite. And so hydroboration, which won H.C. Brown the Nobel Prize, ends up adding in an anti-Markovnikov sense. In other words, if you treat an alkyne with borane or a borane derivative, BH3, and then you carry out an oxidative workup with sodium hydroxide and hydrogen peroxide, you end up adding in an anti-Markovnikov sense to get the corresponding aldehyde. Anyway, your textbook gives a few more reactions and does a nice general survey of synthetic reactions, but I think it's really all review. All right, what I would like to do at this point is to really get us into the meat of the material. And the meat of chapter 21 is going to be what I alluded to at the beginning of class, this addition of nucleophiles. And one of the concepts that I've been harping on and will continue to harp on is the notion of pKa as a way of thinking about strength of a base or strength of an acid or strength of a nucleophiles. So when I think about the reaction of carbonyl compounds, and particularly ketones and aldehydes with nucleophiles, in my mind, I sort of group nucleophiles into different types. I think, for example, about some nucleophiles as being very basic, let's say very strongly basic. We've already seen examples of this. R- alkyl nucleophiles, Grignard reagents, and organolithium reagents. Of course, these are not naked carbanions. They're covalent bonds between magnesium and carbon or between lithium and carbon. But you can think of them from a mechanistic point of view as R-. Ditto things like hydride nucleophiles. And again, typically we're not talking naked hydride. We're not talking about H- as a free species. We're talking about hydride in lithium aluminum hydride or in sodium borohydride. Nevertheless, these end up reacting in many ways like H-. And when I think about these nucleophiles, I think, okay, if I were to think of the conjugate acid of the nucleophile, RH, for an alkane, I would remember, oh yeah, it has a pKa of 50. An alkane is a very weak acid. It's not an acid that if I pour it into water, I'm going to measure any protons, any acidity. The water will still be pH 7 if I put an alkane into water. Well, it wouldn't dissolve, but if I could dissolve it, it wouldn't affect the acidity. But if I had a strong enough base, I would need a very, very, very strong base to pull off that proton. Ditto, the conjugate acid of hydride is hydrogen. The pKa of hydrogen, and I'll put tildes here, I'll put approximately, the pKa of molecular hydrogen is about 35. Then, by comparison, I might think of, let's say, from very strongly basic to moderately strongly basic. And these are all loose categories. But for moderately strongly basic nucleophiles, I'll think of things like hydroxide anion and alkoxide anion, and amines, RNH2 for a primary amine, and ditto I can think of a secondary amine as R2NH, and cyanide anion. Now, all of the conjugate acids here fall in the realm of what you would typically call a weak acid. They're things that you would think of as being a little bit acidic, but not strongly acidic. The pKa of the conjugate acid of hydroxide, the conjugate acid of hydroxide, of course, is water. The pKa of water is 15.7. The conjugate acid of alcohols is just about the same, maybe a hair weaker, depending on the alcohol, about 16 to 17. The conjugate acid of amines is ammonium salts, RNH3+ for a primary amine, or R2NH2+ for a secondary amine. The pKa of a conjugate acid of an amine, of an ammonium ion, is on the order of 10 to 11, sometimes a little higher, sometimes a little lower, but that's a reasonable number. And the last one, hydrogen cyanide, which is actually where we'll start our discussion of reactivity because it has a nice simple reactivity. Hydrogen cyanide is often called hydrocyanic acid, is a weak acid with a pKa of 9.4. All right, so that takes care of what I'd call very basic and moderately basic nucleophiles. And you could probably predict that there would be others in that category, things like hydrogen sulfide, where you have a similar sort of pKa. But this is plenty to get us started. Then, at the other end of the spectrum, we come to what I'll call weakly basic nucleophiles. And by that point, we're talking about things like water and alcohols. It's very important to remember, water and alcohols are amphoteric compounds. So there's actually two pKa's to keep in mind. If I'm thinking about water as a base, not as an acid, as we just did, but as a base, I need to think of the conjugate acid of water, the hydronium ion, H3O plus. The pKa of the hydronium ion is negative 1.7. If I want to think about the conjugate acid of an alcohol, the conjugate acid is ROH2 plus. Now we're talking negative 2 to, and again, these are sort of approximate values, so I'll use a little tilde, approximately negative 2 to negative 3. All right, I'd like to start the discussion of the reaction with the reaction of strong nucleophiles, the reaction of aldehydes and ketones with strong nucleophiles, and start with something with which you're quite familiar because we've been talking about it for a while, and that's the reaction with various types of alkyl nucleophiles. So let me take sodium acetylide. Sodium acetylide, as I mentioned before, is one that you probably can think of as more ionic than covalent. So it's sort of a nice analogy. Acetylene's pretty special. Acetylene, remember, we have an sp2 carbon, so whereas alkanes have a pKa of about negative 50, and alkenes are still kind of similar, 44, By the time you get to alkynes and you have all that S character in the CH bond, the CH bond is reasonably acidic. Acetylenes are -25. So sodium acetylide is still a very strongly basic nucleophile. And if I treat acetone with sodium acetylide, and then I carry out an aqueous workup with some acid, you could write it as H3O plus, or you'd go into the chem stockroom and you'd get some sulfuric acid and some water, or some hydrochloric acid and some water. Your alkyne adds, your alkyne anion adds, and the overall result is an alcohol. That's a reaction that you've seen in the last chapter, and you've also seen SN2 displacements of alkynes before on halides. So now let's think about an analogous reaction of hydrogen cyanide. And I'm going to write this first sort of in a way that may not be so obvious why the reaction is analogous. But if I treat my alkyne, my acetone with hydrogen cyanide, maybe a little bit of base as a catalyst, we have an equilibrium to form a cyanohydrin. The hydrogen cyanide adds in to the acetone, and we get a product that really in many ways looks very analogous to the addition of acetylene. Now, hydrogen cyanide is not something you want to work with. It is probably the most poisonous commonly encountered compound in the organic chemistry laboratory. Hydrogen cyanide is typically fatal at 50 milligrams. It's a gas, or more specifically, it's right on the edge of a gas and a liquid. Its boiling point is 26 degrees. If you've ever worked with methylene chloride or with ether in the chem lab, you know how volatile those are. If you spill it, it evaporates immediately. 26 degrees evaporates basically right at room temperature, so it's practically a gas, which means it's very easy to breathe in 50 milligrams. So only slightly safer is to not work with hydrogen cyanide as a gas, but to work with a solid cyanide source, an acid. If we take sodium cyanide and sulfuric acid, you generate hydrogen cyanide in situ. And so it's equivalent, but at least you're not trying to dispense this half liquid, half gas, this thing teetering on the edge. And this is a very good way to add cyanide to a carbonyl compound, to a ketone or aldehyde. Sodium cyanide is nasty stuff. This was used in the gas chambers in Nazi Germany to kill people by this very reaction, and it used to be used in our gas chambers to kill people, where you would mix it with sulfuric acid. So this is not nice stuff to work with. It's very poisonous. But from a chemical point of view, what we've done here is very cool. We formed a carbon-carbon bond. And this is the basis for building up, one basis for building up much more molecular complexity by forming carbon-carbon bonds from simpler molecules.
Just out of curiosity, what mechanism does cyanide do to harm us?
What mechanism does cyanide do to harm us? I believe it binds to your hemoglobin.
Oh.
So cyanide, carbon monoxide, nitric oxide, I think all can bind to your hemoglobin to various degrees, but it's a nasty, nasty poison. However, I thought you were going to ask, what mechanism does it add to the carbonyl compound? And that question is one that actually brings us to the heart of of the mechanistic chemistry that we're talking about. So we can think about this mechanism as involving cyanide as a nucleophile. And cyanide is a good enough nucleophile to add directly to a carbonyl compound. So hydrogen cyanide is in equilibrium with cyanide anion. Sodium cyanide and sulfuric acid is in equilibrium with cyanide anion. And so cyanide anion can add to the carbonyl compound like so. Just as we've seen before, electrons flow from the nucleophile to the carbonyl carbon, from the carbonyl double bond up onto the oxygen. You add, you form an anion, an oxyanion. And then in a second step, that oxyanion can protonate, and I'll write it as protonating from hydronium ion. Could protonate from another molecule of HCN as well. Electrons flow from the oxyanion to the hydrogen. That in turn pushes electrons out of the OH bond back onto the oxygen. And we get our cyanohydrin. So what you can see here really is a big degree of analogy between the chemistry that you've seen thus far, where we've added an alkyl metal, and this new chemistry where we're just adding a moderately basic nucleophile. Your moderately basic nucleophile exists as an anion. It can add to the carbonyl. You get an alkoxide anion. The alkoxide anion can be protonated. The only big difference is with a strongly basic nucleophile, you can't have your proton source present at the same time because the strongly basic nucleophile would react with your proton source and would be quenched, whereas the moderately basic nucleophile can exist in equilibrium with the protonated form, and so you don't have to worry about it being quenched. All right. Your textbook pedagogically does something that was very interesting at this point. And at first it sort of surprised me, and then I thought about it, and it made sense. So the rest of this chapter is going to set us up for more complex reactions. It's going to set us up for the formation of imines, the formation of acetals, formation of hemiacetals as well, the hydrolysis of imines, the hydrolysis of the formation of enamines, and all of the reverse reactions. And at this point, your textbook introduces a reaction that's a little bit of an oddball. It introduces the Wittig reaction. And when I thought about it pedagogically, it actually made sense why they're doing this. I think very few textbooks introduce the Wittig reaction at this point. The Wittig reaction is the reaction of a ketone or an aldehyde with a phosphorus ylide to form an alkene. I'll write this out in just a second. But the gist of the reaction is that a nucleophile is adding into your ketone or aldehyde, and ultimately we're pulling the oxygen out and replacing it fully, not half replacing it or adding to it as we did here, but we're replacing it fully with the nucleophile. And that theme is going to come up in the rest of the chapter in the formation of acetals, in the formation of enamines, and in the formation of imines. So let me write out the reaction and explain how it works. So we have a ketone or an aldehyde. We have a carbon nucleophile called an ylide. And I'll write out the structure. Invariably, it's a phosphorus ylide. An ylide, so this is called a Wittig reagent. An ylide is a species where you have a separated positive and negative charge. And so we call this a phosphorus ylide, because we have the separated positive and negative charge on phosphorus. And the overall reaction that occurs here, again, in very generic form, is that we now replace the oxygen to get an alkene. And as a byproduct of the reaction, remember, organic chemists hate writing byproducts of reactions, you get triphenylphosphine oxide. Triphenylphosphine oxide is not only something that's easy to forget about as a byproduct of reaction, it's also a pain in the neck to get rid of if you're carrying out the reaction in the laboratory. All right, there's a lot of anatomy here. One of the things you'll find is in shorthand, we often write pH as a phenyl group. So I'm going to write things out in longhand now for the conjugate acid of the phosphorus ylide. The conjugate acid of the phosphorus ylide is a triphenylphosphonium salt. And I'm writing the benzenes explicitly so you can see at least one time what we will, for the rest of today's lecture, be writing out as pH. And the main thing is, in the phosphonium salt, you have a proton, and that proton is acidified by the positive charge and the stabilization that phosphorus provides. So the proton is acidified. Its pKa is about 22. In other words, it's right in that range, kind of like acetylide, or kind of like acetylene as far as its pKa goes. It's at that very sort of lower edge of strongly basic. And there are two things that are super stabilizing about this phosphorus. One thing that's stabilizing about the phosphorus is, of course, that you have the negative charge next to a positive charge. The other thing, and I'll write out my phenols explicitly for a moment here. pH, pH, pH. The other thing that's specially stabilizing about phosphorus is in that row of the periodic table. It's down from the row from carbon and oxygen and nitrogen and fluorine. It's in the row of periodic table where you can invoke d electrons, where you have d orbitals. And so we can write a resonance structure that has more than 8 electrons around the phosphorus. And together, these two resonance structures make up a more complete structure of the phosphorus ylide. So for these two reasons, we have a good degree of stabilization, a good degree of acidification of this proton versus what you would expect for a plain old alkane, which would have a pK of about 50. All right, so let's go on to talk about the mechanism of this reaction. You can think of the mechanism of this reaction as occurring in just 2 steps. Or you can think of it as occurring in 3 steps. Your textbook writes it in 2, and I'm going to write it in that way and tell you why it's been of so much concern for people. So you can envision that in the first step, your phosphorus ylide has a nucleophilic carbon and an electrophilic phosphorus. And so two things can happen at the same time. Electrons can flow from the nucleophilic carbon to the electrophilic carbonyl carbon atom. And at the same time, they can flow up onto the oxygen, but form a bond with the phosphorus. So I should say we can go ahead and have our electrons flow like so, forming a four-membered ring called an oxaphosphatane. I'll write out the name for it. And this is an intermediate that actually can be observed experimentally. It's been debated in some detail whether this reaction occurs in a concerted fashion, meaning both of these bonds are formed at the same time, or whether they form first with a carbon-carbon bond and then in a second step with an oxygen-phosphorus bond. And consensus from experiment and calculation seems to be on the concerted, coming down toward the concerted mechanism. But in some textbooks and in some places, you will see an intermediate written out. Where we still have charges separated. In other words, where one bond has formed before the other. This intermediate is called a beta-ene. And I have personally seen people yelling at each other over the distinction in mechanism. For your purpose, it's not so important. The reason this reaction has been so hotly debated is it exhibits some stereoselectivity toward forming a cis-alkene. Just a little bit of stereoselectivity, but enough to raise people's attention, and for this reason also a lot of interest. In a second step, the oxaphosphatane breaks down, and the oxaphosphatane breaks down again in a concerted process, giving rise to the alkene and triphenylphosphine oxide. Like so. And so through these two steps, addition of the phosphorus ylide to the carbonyl to form an oxaphosphatane, and then breakdown of the oxaphosphatane to the alkene and the triphenylphosphine oxide, we can go ahead and form a new carbon-carbon bond. Question?
Yeah, one like the two molecules are fused in that box. Wouldn't the substituents like to be in a trans position rather than a cis position to be as far away from each other as possible?
The two substituent, which one? Here?
The four substituents, sorry.
The four substituents. So one of the substituents is pointing out, one is pointing back, one is pointing out, one is pointing back. And getting well beyond the scope of the course, and you can read more for starters on Wikipedia and the article cited there, is this issue of why in certain circumstances you prefer to form the cis species. But I'm going to skip that for now because it gets well beyond the scope of the class. All right, I want to talk at this point about what one can do with it. This is an incredibly powerful synthetic reaction. We've just formed a carbon-carbon bond, a carbon-carbon double bond, stitching together two halves of two pieces to make a more complex molecule. That's powerful, and it's interesting, and it's mechanistically interesting, And for that reason, George Wittig won the Nobel Prize in 1979 for the discovery of this reaction. Let's just take a look at how one does this in practice. So I'll show a couple of examples. Let me show how I do a Wittig reaction of cyclohexanone. And so first, I will go ahead and just show you the reaction of the phosphorus ylide, and I'll write it in the other resonance structure. Both of them are correct. If I mix the phosphorus ylide and cyclohexanone, this is the phosphorus ylide derived from ethyl, so I get the ethylidene compound. I've added in these two carbons, and the other byproduct of the reaction is triphenylphosphine oxide, like so. Now, in practice, the way one carries this reaction out in the laboratory is you go ahead and you make the phosphorus ylide yourself. Triphenylphosphine is a good nucleophile. You can take an electrophile like ethyl iodide and mix them, and you get ethyl triphenylphosphonium iodide, PH3P, CH2, CH3 plus, I minus. And now, again, in the laboratory, you would then make your own ylide. You would go ahead and you would treat your ethyl triphenylphosphonium iodide with a strong base, like butyl lithium. I'll write in butyl lithium to indicate it's the normal isomer 1-butyl lithium. Sometimes you just write butyl lithium. Or you could use sodium amide. Both of them are strong enough bases. Remember, the pK of the conjugate acid of butyl lithium is, the conjugate acid is butane, pKa 50. The pK of the conjugate acid of sodium amide is ammonia, pKa of 38. So they're both good enough bases to do it. So they will generate our phosphorus ylide, our ethylidene triphenylphosphorane, it's called. And so that's kind of neat. I want to close by comparing and talking a little bit about selectivity and why this reaction is so powerful, why the Wittig reaction is so powerful. And so I want to offer a comparison to the elimination reactions that you've learned about, the E1 and E2 elimination reactions, and we'll just look at an E1 example. If we wanted to make this same alkene by doing an E1 elimination reaction, I might imagine starting with cyclohexanone and treating it first with ethyl magnesium bromide, and then doing an aqueous workup to give the corresponding alcohol. And now, if I were to treat this alcohol with sulfuric acid, maybe a little heat under dehydrating conditions, sure, I'd get some of this product that I set out to make by the Wittig reaction, but I'd get it as a mixture of products in which we would also get the internal alkene. And so much of organic chemistry is about synthesis and about control. And the control that the Wittig reaction provides is very, very powerful. Now, as I hinted at before, the other element of control, and it's only partial control, is that under certain conditions and in certain circumstances, you can preferentially get the cis-alkene. So if we have a monosubstituted Wittig reagent, in other words, a Wittig reagent that has just one R group on it, and we have an aldehyde, and we allow them to react, we get a mixture of products the cis and trans alkene. It's pretty hard to get just one pure. Well, you can sometimes get the trans pure. But the trans isn't surprising because trans alkenes are more thermodynamically stable. But what's interesting is that sometimes, under some conditions, the cis product can be the major product. And this is surprising because it's contra-thermodynamic. The more stable alkene is the transalkene. In the cis-alkene, the two substituents bump into each other. If I have cis-2-butene, the two methyl groups gently bang into each other, but cis-2-butene is about 1 kilocalorie per mole less stable than trans-2-butene. And in part because of this surprising property of the Wittig reaction, people have yelled at each other and debated and studied the mechanism in tremendous depth. Next time we will pick up by talking about other reactions. We'll talk about imine formation and enamine formation and their mechanistic reverse.